channel. Today's class I am going to discuss about how to implement the logic gate using only NAND gate. So this is very important topic in digital electronics. Now we move on the session. So first I write the list of logic gates. NOT gate, AND gate, OR gate, NAND gate, NOR gate, XOR gate, last one XNOR gate. So in this session I am going to implement this logic gate using only NAND gate. So using only NAND gate we will discuss one by one. So let me take NOT gate. So it's a single input gate. Now I draw the symbol. So it's a symbol of NOT gate. Input is A, output is A bar. So let me assign the A value equal to 0. So output of the NOT gate is just taking complement of input. So A bar value equal to 1. Now I am going to implement this NOT gate using only NAND gate. So first I draw the symbol of NAND gate. So this NAND gate is 2 terminal, but the inverter is a single input. So that input namely called as A. I just short this 2 input. This A value is connected here. So first terminal input is A, second terminal input also A. Output of the NAND gate is A dot A the whole bar. You just apply the Boolean rule. A dot A represent A. So the final output is A bar. So here input value A equal to 0. So let me assign the same value A equal to 0. So 0, 0. The corresponding output is 1. So A bar value equal to 1. It produces the same result. So it's a equivalent NAND inverter. Then come to the second gate, AND gate. So it's a 2 input logic gate. So it's a basic symbol. Inputs are A and B. The corresponding output Boolean expression is A dot B. So A dot B is the corresponding Boolean expression of AND gate. Now I am going to implement this AND gate into NAND gate. So here input of the NAND gate is A, B. Output is A dot B the whole bar. So A dot B the whole bar is the first NAND gate output, but I get only A dot B. So I am using one more inverter. So this output is connected to the input of the second NAND gate. Now the expression is A dot B double bar. So this bar cancel. The final answer is A dot B. So both the Boolean expressions are same. Here I apply the input value for A and B is 1, 1. The final output is 1 dot 1, 1. So here also I apply the same input, A value equal to 1, B value equal to 1. So output of the NAND gate is 0. So this 0 is applied to the second NAND gate input. The final output is 1. Output wise both are same. So next one is OR gate. First I draw the symbol of OR gate. A and B is the input. The output of the OR gate is A plus B. Now I am going to implement this OR gate using only NAND gate. So NAND gate means the operator is dot operator, but here plus operator is present. So first I change this plus into dot operator. So in that purpose I am taking double bar in the expression. Now I apply the De Morgan's theorem, break the bar, change the sign. A bar dot B bar the whole bar. So using this expression, now I am going to draw the NAND logic. So actual input of the circuit is A and B, but I need A bar and B bar. So this A value is connected to NAND inverter. The output of the inverter is A bar. B is connected to next inverter. Output of the inverter is B bar. So far we get A bar and B bar. Now I am going to take the product of these two variables, then complement. So in this operation I am using one more NAND gate. So this A bar is connected to first input, B bar is connected to second input. Output of this third NAND gate is A bar dot B bar the whole bar. So these two expressions are same. So I just apply the De Morgan's theorem. So A bar bar plus B bar bar. So these two bars are cancelled. The final expression is A plus B. So next one, NOR gate. First I draw the symbol of NOR gate. The input is A and B. Output of NOR gate is A plus B the whole bar. So this NOR gate is implemented using only NAND gate. I already told NAND gate in the sense a dot operator is present, but here plus operator is present. So this plus is changed into dot operation. In that purpose, I am taking double bar in the expression. Now I am going to apply the De Morgan's theorem. Break the bar, change the sign. So A bar dot B bar, then double bar. A bar dot B bar, then double bar. So using this expression, now I am going to draw the NAND logic. So actual input is A, but I need A bar. So I am using one NAND inverter. So output of the NAND inverter is A bar. Then second input is B, but I need B bar. So this B is given to second inverter input. Output of the inverter is B bar. So far I obtained these two values, A bar and B bar. Then I am using one more NAND gate for getting product of these two variables, then complement of this variable. So A bar dot B bar the whole bar. So far I obtained A bar dot B bar the whole bar. So this bar is bending. So I am using one more inverter for getting the double bar. So A bar dot B bar, then double bar. So it's a final expression. So these two expressions are same. How I said it? Just I simplified this expression. A bar dot B bar, then double bar. I just apply the De Morgan's theorem. Break the bar, change the sign. A bar plus B double bar, then whole bar. So this bar cancel. The final answer is A plus B the whole bar. These two expressions are same. So remaining these two XOR gate and XNOR gate we will discuss in the next video. I hope you understand this concept very well. If you are watching first time in my video, kindly subscribe and support us to make a lot of videos. Thanks for watching my channel. Thank you.